and one of the major advances in light microscopy over the last several decades. So the second kind of aberration is monochromatic aberrations. And monochromatic aberrations are those that occur even if you only have one wavelength passing through the material. And an example of one of the 5 major monochromatic aberrations is shown here. This is spherical aberration. And this comes from the fact that even though spherical surfaces are the easiest to make, the sphere is not the perfect focusing shape. In fact, you need different shapes, aspheric shapes, in order to perfectly focus a given wavelength to a spot. But for large focal lengths, spheres tend to do a very good job, and spherical aberration is not as bad. And so again, the concepts of thin lenses, where we only care about the index and the rays of curvature, those concepts are still useful in thinking about how imaging systems work. Okay, so let's build up our skills so that we can actually identify where the image of an object will show up on one side of the lens. So we're going to learn 3 tools of the trade, and those are ways of identifying where rays should go, where these representations of rays should go from a given point on an object. So if you think about an object as being something that is scattering light or emitting light, we have the option of picking a number of different rays coming from that and asking where do those go. So what we're going to do is we're going to be smart about picking rays that do things we know. And the first is that any ray that comes in parallel to the optical axis is this line all the way along the center of the imaging system. That optical axis, if the ray comes in parallel to it, the ray should converge through a positive lens through the focal point. Or if the ray comes in at an angle, it will still converge through the focal plane, but offset from the optical axis. So that's one very helpful rule. Parallel rays coming in go through the focus. The second helpful rule is just the opposite of that. If you have light coming from a focus, it will leave this lens as parallel rays. So you can imagine that those are the case because you could run these 2 diagrams if you flip them around, they're the same. So there's one last rule of thumb for ray tracing, and that is rays that pass through the center of the lens are not refracted. So in reality, they are refracted a little bit, but the refraction is opposite. So you bend it one way and then you bend it back the other way, so it comes out looking as if it hasn't been refracted at all. So those 3 things: rays coming in parallel pass through a focus, rays coming from a focus come out parallel, and any ray that passes through the middle of the lens isn't bent at all. So we can now use that to figure out where should an image show up if we have a lens in front of this object. So we'll start by tracing a few rays. So these rays are all coming from the tip of the object. So let's take this the middle ray. So the middle ray is passing all the way through the center of the lens, and based on that rule number 3, we shouldn't bend it at all. That ray should pass all the way through and continue going. Now if you look at the bottom ray, that bottom ray is coming from the tip of our object, but we've chosen it so that it passes through the focal point of our lens, so the front focal point of the lens. And what that means is that when it hits the lens, we know it must be coming out parallel to the optical axis. So the optical axis is, again, this dotted line here. So where those 2 rays converge, that is where the tip of our image must be. The rays that came from that tip, the lens is converging them back to that tip, and that's what allows us to do the imaging. And that third ray is one that doesn't follow either of our rules, but we know that any light coming from that tip must end up at its conjugate point on this other tip. So these 2 planes, the object's plane and the image plane, are known as conjugate planes, and the points within them from which light comes and to which light goes are conjugate points. Now we can take other points on that same object and make the same sets of arguments, that rays passing through the middle of the lens don't bend, rays that pass through the focus come out parallel, and we can identify the other part, the other end of this object, as well as each point in between. And this, we've used drawing essentially to figure out where things ought to go. But this drawing is a shortcut for some relatively simple math, which can also be used to calculate where an object and image are. So the two equations that are worth remembering: one is the thin lens equation, which relates the distances from the object to the lens, and that's denoted SO, and the distance from the lens to the image, that's denoted SI. And those 2 quantities are related to F, the focal length, by this thin lens equation. So that will tell you where, for a single positive thin lens or for a negative lens, where does the image show up. The second equation is magnification. Oftentimes, especially in microscopy, we want to know how big something is, or we want to make it a certain size. We want to increase its size so we can see detail. The magnification is, by definition, the transverse magnification is the ratio of the heights of the object and image, and those, it turns out, are related to the distances of the object to the lens and the image to the lens. Now, I'll point out one other thing, and that is when the object is in place, the focal length we're not placing the object on the focal plane. So when we say something is in focus, we don't always mean that the object is in the focal plane. We simply mean that we are getting an image which is good quality. So focus, that distance F, isn't the place where you always put the object. We're talking about a case in which you can put an object there, but then you need another lens in order to form the image. So we'll do another quick demonstration about how to think about lenses forming images and a couple of examples. For this demonstration, we'll look at the properties of positive lenses and their ability to form images. So I've got 4 things here. One is the same light source I used before. It's connected by a fiber optic cable to a collimator. A collimator is simply a single lens that takes the light that is emanating from this fiber and creates a parallel collimated ray. So much like the diagrams in which rays that are passing parallel will be converged to a focal point by a positive lens. So we can test that out simply by taking a lens, these are 2 lenses, take one of them and move it in the path of the light. And what we would expect to see is at some position past the lens, there should be the spot of tightest focus. And we can identify that using a simple piece of paper and moving that from the lens position until we see the tightest spot. And now we see it expanding again, and tight, and expanding again. And this is often a simple way of figuring out what lens you have. If you have a lens in a drawer and you want to know what is its focal length, being able to take a light source, even overhead light, and position it such that that overhead light is in focus, we're finding the minimum spot, and then taking a ruler and measuring what that is, you can get an estimate of the focal length of the lens. Now, just converging the rays to a focus is a good start, but really we want to converge rays to a focus from an object of interest, so from a sample. So let's add one more thing to this system, and that is a tiny little cross. So this is an opaque surface of glass that has a small, thin cross that allows light through. And if we put this object at the focus of the lens, it's being illuminated by this light put at the focus of one lens. Those parallel rays that are coming from different spots on that cross are coming through this lens. And if we look at where the light is, we can see initially there's a nice circle rather of intensity, and that circle of intensity is going smaller and smaller and smaller and smaller. And then right where we found the smallest circle of light from the focus of the lens, we see the image of that cross. That image of the cross, if you go above it, it blows out. If you go below it, it blows out. And it's interesting to note how uniformly illuminated this is. You wouldn't know if you looked at that intensity that this is a cross, or rays from a cross. It's only at the position of best focus where you see the cross. Now, we also know that you can put lenses together and increase magnification or change the location of images. So what if we add a second lens to that system? So we've taken an object, we've created an image. If we add another lens, we should be able to use this as the object and create an image. So if we look at the wall, and if we adjust the position of this lens, we've now created an imaging system where I have a two-lens system. I've taken one step to change the size of my cross. This is actually demagnifying a little bit, and this is magnifying. So the size of this cross is substantially smaller than that one, and based on our lens maker equation, we should be able to determine, based on the focal length of the lens, the separation between the object and the image. We should be able to calculate that, and similarly, we should be able to get the magnification out of those by the ratio of the distances. Okay, so hopefully now you believe that when you have a single lens, you're able to control the angles at which light is propagating, and you're able to form an image from an object. Now let's take a few harder cases. So ones in which we move an object into places that don't create a real image. So we call images where the light actually converges and creates an intensity pattern. We call that a real image. And those are the kinds of images that we put onto CMOS cameras. Those are the kinds of things that we record because we want to be able to know what that intensity distribution is, and real images are required for that. But in some situations, for example in eyepieces, we want to create virtual images. And an example of creating a virtual image is shown in the lower figure. And the way you can accomplish this with a positive lens is to move the object inside of the focal distance. So for your SO to be smaller than your focal distance. And what that means is that the actual rays coming from this object are going to diverge coming out of the lens. But if you trace those rays back, the object or the image that they appear to be coming from, if you didn't have the lens there at all, it appears that the light is coming from a virtual image. So that's the concept of a virtual image. Your object is real, but you're creating a virtual image that someone looking at this didn't know that there was a lens there. They would think it's coming from that virtual image. So the same can be done with negative lenses. You have an object and you create a virtual image because the negative lens, wherever you place the object, is going to diverge the rays, and again tracing those rays back where they appear to come from is the virtual image. And you can conversely use a negative lens to take rays that are converging and move the position of the image formation so that it creates a virtual object. That's shown in the lower picture. So with a basic understanding of waves, and how they move through surfaces, and how you can shape surfaces in such a way as to control where the rays go, you can start to assemble combinations of lenses so that defined curvatures of multiple lenses can be used to take light from an object and reform it into an image through a set of lenses that eventually, when you add all of the special features that we need for microscopy, become the modern research microscope. And that's the objective here, is to introduce you to the very fundamentals of light and image formation so that you can begin to understand what exactly is the microscope doing. So just to review, we talked about the properties of light, its wave nature, and the different properties that allow us to work with it and for it to generate contrast in samples. We talked about light-matter interaction, refraction and reflection most importantly, and how with refractive lenses you can control the curvature, the shape of these lenses, and define where an object in an image would be. And finally, this image formation can be achieved by controlling those positions and assembling sets of lenses that give the desired magnification with the desired resolution. So that's our first step towards understanding what's inside. And I'm going to follow up from the last lecture where we talked about how lenses work, and now discuss how lenses are used in a microscope, specifically how they're used to focus light from the specimen so that you can see it either with your eye or the camera, and also how we use lenses to collect light from a light source and focus it on the specimen using a technique called co-illumination. And finally, I'm going to discuss the conjugate image planes of the microscope. Well, before we start discussing the lenses in the microscope, let's just review some of the features of lenses that we learned about from the first lecture. So here we have an object. This object is narrow, and we're going to place that object to the left side of the focal plane of this particular lens here. And the object is going to be emitting light here. Some of that light is collected by this lens. lens, you can predict where the image will form on the right side of the lens. And the magnification that's created by the lens, well, by definition, is the size of the image divided by the size of the object, which is also proportional to the distance of this image away from this lens divided by the distance of the object from the lens. Now, just as a review, there are two other key points about lenses that I would just like to cover again because they're very important for understanding how these lenses work in the microscope. So one key point about how lenses work is that a parallel beam of light coming into the lens, as you see here, comes to a focus at the focal plane of this particular lens. In fact, that's the definition of the focal plane. So parallel light comes to a focus on the other side, and conversely, light that is diverging from this focal plane over here passes through the lens on the other side as parallel light. And we'll see how this comes into play in the way the optics work in the microscope. So the most important lens in your microscope is the objective lens, which I'm showing over here. And I'm depicting it here as a pretty simple, thin lens. In reality, as you'll hear from the next lecture, which is devoted to objective lenses, it's actually quite a complex series of lenses that are put together. But here I'm just simplifying that into a simple lens. And if you bought an objective lens or have a microscope that is from the 1970s or 80s, it works by a principle of finite imaging. In other words, this lens works pretty much like the lens I just showed you a couple slides ago, where the specimen or your object is placed a short distance away from the focal point of this objective. And then light travels through this objective lens. Here's the tip of the arrow coming into focus, the middle and the bottom of this arrow, which is all focused by this objective lens to create an image on the other side at a fixed distance away from that objective lens. And for many microscopes that were built in that era, that distance is about 160 millimeters. Now, if you have a microscope that you purchased more recently, like in the last 20 years, those objective lenses and those microscopes work using a different optical system, using infinity objectives. And the way this works is now the object, your specimen, is placed exactly at the focal plane of this objective lens. And as we just discussed, light coming from the focal plane from your specimen will travel through this objective lens on the other side as parallel light. So here's light coming from the top of this arrowhead, the middle and the bottom, all emerging on the other side as parallel light, which obviously is diffuse light. It's not going to create an image. So you need to have another lens in this system, which is the tube lens, such as shown here, which now takes this parallel light and refocuses it to create an image on the other side. So one reason why manufacturers have tried microscope and where you place the tube lens, because all this light is traveling parallel, so you can place this tube lens in different points of the light path. And that allows you also flexibility for putting case, the magnification of the combination of these two lenses is given by this formula here, which is the focal length of the tube lens, which is usually a big number, divided by the focal length of the objective lens, which is usually a much smaller number, and that gives you the degree of magnification of the system. Okay, so how do we actually see this image? Well, there are two ways. One is to view it with your eye, and through an eyepiece. The way this is typically done is the light comes from your specimen here. It's focused through these two lenses that we just talked about, the objective lens and the tube lens, to come and produce an intermediate image. But we're now going to put another lens system here that can further magnify this intermediate image and produce greater magnification by going through an eyepiece. And we're going to have a short lecture where you can learn more about how these eyepieces work. And then through another lens, which is actually the lens of your eye, to create a final image on your retina, which is your detector. So here we have different points of your specimen all traveling through this optical system to be focused on your retina to create this final image that you can see on your retina and processed by your brain. Now the other way to capture your image is by using a camera. And the simplest approach for that is just to place the camera at the intermediate image plane. So again, here we just learned that light coming from your object travels through the objective and tube lens and comes into focus here from different points in the object, and this is the intermediate image plane. And we can just place a camera right at that intermediate image plane, and the detector now will be able to record this in-focus image. And for many cases, the magnification that you achieve through the objective and tube lens is sufficient. And we'll talk about how to optimize the proper magnification for particular cameras later on in this lecture series. In some cases, you may want to magnify the image more, in which case you can now introduce a projection eyepiece that again collects the light that's coming through this optical system from this intermediate image plane. It diverges, it's recollected by this eyepiece, which gives you additional magnification, and then ultimately focused on the camera. So we've just covered now how lenses are used from the specimen to create an image either on a camera or through eyepiece onto your retina. Now lenses are also used to illuminate the sample as well, to collect and focus light from a lamp. And you'll hear additional special lecture on different kinds of lamps that are used in microscopy. And we need to collect and focus that light onto the specimen. And for transmitted light, the best way to illuminate the specimen is using a technique called color illumination. And the way this works is that you have your light source over here, and the light source is first goes through a collector lens, which is usually placed very close to the light source. Many microscopes also have an additional lens called a field lens. But the combined goal of the collector and the field lens is to focus light coming from the lamp, from point sources on the lamp. The light gets focused to a plane, which is the front focal plane of the condenser lens. So there's a condenser lens over here, and the front focal plane is usually right at the bottom of this condenser lens at an aperture that I'll describe later. And we just learned that if light is emanating from this focal point at at the focal plane of this lens over here, it's then going to travel through the lens on the other side as parallel light. So here we have parallel light illuminating the specimen. And we're going to have a special laboratory where we're going to discuss, in fact, how to adjust all of these lenses to achieve correlative illumination. But the contrasting way of illuminating a specimen is called critical illumination. And in this case, instead of having defocused parallel light at the specimen, critical illumination focuses light from the lamp directly onto the specimen. So the image of the light source is projected onto the sample itself. Now this can focus and create a very intense illumination at the sample plane. But because it creates an image of the lamp may have very uneven, may have a filament, it may be very uneven, and that creates uneven illumination of the sample. So the main reason for using critical illumination is to generate uniform light intensity of the specimen. Even if the light source itself may be somewhat non-uniform, by defocusing it and having parallel light, you can generate the best type of even illumination possible. So anyway, let's go to the microscope now and have a look where all of these lenses are in a real microscope. Okay, so now let's look at where the lenses are in the real microscope over here. So let's first of all start from the lamp. So here we have the illuminating source, it's this filament here, and then we have a lens in front of that, which is a collecting lens for the light, and that light then travels through this part of the microscope. And in the top part of the microscope, there's a second lens, which is our field lens. And if we turn it upside down, you can then see this piece of glass, which is the field lens. And the combination of the collector lens and the field lens are used to focus the image of the lamp onto the front focal plane of the condenser. So that's the next lens in the system, so let's look at that one. Let's take out our collector lens over here. We can slide it out. And so if we look at the front part, this is the condenser lens itself over here. And the front focal plane of this lens is where an iris is placed. This is the condenser diaphragm. And we can open and close this diaphragm. So the image of the light source is focused onto this part over here. And light coming from the front focal plane of the lamp, like the condenser lens, will then travel on the other side as parallel light, which is illuminating the specimen. So then the next lens in the system here is the objective lens. We'll have a whole lecture on objective lenses, but this just shows the objective lens over here. And then the objective lens is used in conjunction with the tube lens that we talked about. The tube lens is kind of buried in the body of the microscope, so I can't show it to you. But light collected from the objective and the tube lens is then either focused onto the CCD chip of the camera over here, or there's an image created just in front of the eyepiece, and the combination of the lenses of the eyepiece with the lens of your eye is then used to create an image of the specimen on your retina. Okay, so the last point I'd like to cover in these lectures are conjugate planes in a microscope. And conjugate planes are different planes or locations in this microscope system that are in simultaneous focus. And when you view these planes through the microscope system, they appear to be superimposed and in focus with one another. And let me illustrate this with some examples here. So first of all, we have image-forming planes. So we already discussed that we can view the specimen through this combination of the objective lens and the tube lens, and this creates a focus and an image on a detector such as the camera. Now, below the sample, manufacturers have also placed a field diaphragm, which if the system is set up in proper critical illumination, that field diaphragm gets focused on to the plane of the sample. So there will be an image. This field diaphragm is actually a physical entity. It has an iris, as I'll show you in a second, and it gets focused onto the sample. And in turn, it goes through the objective lens and the tube lens, and the image of this field diaphragm is also imaged on the detector as well. So if we're looking at this aligned microscope through a camera, what we see is the following. If we close down the field diaphragm, we see not only the image of the specimen over here, but we also actually see the image of the iris of this field diaphragm superimposed and in focus with the specimen itself. And by opening and closing the field diaphragm, as you'll see in a second, we can restrict or enlarge the field of view. So now let's talk about the conjugate image planes of the microscope and show you where they are. So first of all, let's discuss the image-forming planes, starting with the field diaphragm. So the field diaphragm is an iris that's in front of the lamp, and in fact, if we take this unit apart here, we can see this iris in the body of the microscope and we can see it open and close. If we adjust the position of this condenser lens appropriately on this rail, we can focus the image of that iris onto the specimen plane. So the image of the iris will be superimposed on the specimen. And the specimen and the field diaphragm, those images will then be projected by the objective lens and the tube lens either directly onto the CCD chip or through a combination of the eyepiece and your lens onto your retina. There's also a separate group of planes that are involved in illumination and chromal illumination. So again, we talked about how the light source is focused through these set of lenses onto the front focal plane of the condenser lens. This is also the location of an iris diaphragm at this front focal plane. And then it comes out as parallel light bathing the specimen, which gets refocused to the back focal plane of the objective lens. And then it travels through and it becomes diffuse again at the detector, so we can't see an image of the light source. But we can see an image of the light source here at the front focal plane of the condenser, and there's also an image of the light source at the back focal plane of the condenser as well. Now note that we can't see the image of the light source on the camera with your eyepiece because we're looking at the wrong focal plane. But if you put another lens in the system, which is often called a portrait lens, or also an eyepiece telescope, instead of focusing on the specimen like we normally do, we can focus on the back focal plane of the objective see an image of a light source.